Tonight, before anything else, let a question drift up out of the dark, one you have almost certainly asked before, perhaps as a child at the very edge of sleep, perhaps more recently in some still hour when the noise of the day had finally loosened its hold on you. It is among the oldest questions our kind has ever framed, and it is short enough to hold inside a single slow breath. What was there before the universe? Before the galaxies wheeled into being? Before the first star kindled in the cold? Before the beginning itself, what was there? Let the question rest in you for a moment, the way you might close your hand around a small smooth stone and feel its weight without needing to do anything with it at all. The question feels entirely reasonable, and that quietly is the first small marvel of the night, because the more carefully you look at it, the less certain it becomes that the question means quite what you think it means. Notice the little word that is doing all the work here. Before. It is a small word, worn soft with use, and you have leaned on it your whole life without it once betraying you. Before breakfast, before you were born, before the rain came, before the light in the window changed, before the year turned over into the next. Every single time you have used that word, there was a river of time already flowing underneath it, and the word simply pointed a short way upstream. Before means earlier, and earlier means there was a clock already ticking, a sequence already unfolding, a stage already set on which one thing could follow another. The word before has never once had to stand up on its own. It has always had time beneath it to hold it up. And here is the gentle difficulty, the one we'll spend this whole long night walking slowly toward and slowly around. When you ask what was there before the universe, you're asking that worn little word to point upstream past the very thing that may have made the stream in the first place. You're asking it to stand somewhere there might be no earlier for it to reach, no clock behind the first clock, no stage behind the first stage. It is a little like walking north and north and north again until you arrive at the very top of the world, and then taking one more step and asking someone which way is further north now. The question has a perfectly good grammar. The words are all sitting in their proper places, and yet the thing the words are reaching for may simply not be there. Not because it is hidden from us, but because the reaching itself has quietly run out of world. Now, if that unsettles you even a little, let it settle again, because this is not a night for unease. This is a night for the particular pleasure of a question that turns out to be far deeper and stranger, and more beautiful than it first seemed. A question that does not so much get answered as gently transformed while you watch. We're not going to arrive at a scene from before the beginning, some dim room you could peer into if only the lights were bright enough. What we're going to do instead is walk backward together, carefully, one honest step at a time, along a path that real people built out of real measurements, and see just how far back that path can carry us, and notice when we reach the far end of it, what has happened to the question we started with. Here is the other half of the puzzle, the half that keeps the first half from being merely a trick of language, because it would be easy to think this is all just wordplay, that the universe surely had some ordinary past like everything else, and we are only tangling ourselves in grammar. But that is not the situation at all. The remarkable thing, the thing that took humanity most of its history to discover, is that the universe genuinely did have a past, a specific and traceable one, and that this past was utterly unlike the calm, eternal backdrop people once assumed. Everything you can see tonight, every distant point of light, was once crushed together into a state so hot and so dense that all of what is now the observable cosmos was smaller than a single atom. That is not a metaphor, and it is not a guess. It is the sober conclusion of more than a century of patient looking, and we can follow the evidence for it backward with real numbers almost the whole way down. So hold the two things side by side, and do not rush to reconcile them, because their quiet tension is where we're going to live for the next few hours. On the one hand, the universe truly had a beginning, or at least a first moment we can meaningfully speak of, a moment we can approach with instruments and mathematics and reach to within the tiniest sliver of the very first second. On the other hand, the word before, when you push it back to that first moment and try to make it point one step further, may have nothing left to point at. Both of these are, as far as we can tell, true. The path back is real. The place it leads to may not have an outside. That is the loop I am leaving open for you tonight, and I will leave it open on purpose, the way you might leave a door ajar in a warm house so that a little of the night can still be felt from your bed. If time itself began with everything else, then what could the word before possibly mean? And what does physics actually find when it walks all the way to that edge? Somewhere far along in our slow descent, that question is going to quietly turn inside out. And the turning is the whole reason to stay. Not because there will be a jolt or a reveal, but because the shape of what you are wondering about will soften and change, the way a familiar room changes when you finally notice where the light is coming from. For now, let the stone in your hand be just a stone. Let the question be just a question, resting there, unhurried. Picture, if you like, a single candle in a dark room, its small flame leaning and steadying, and imagine that flame is the whole of everything we can see, all the galaxies and all the light, gathered for a moment into one gentle point. We are going to follow that flame backward through time, watching it grow hotter and smaller and stranger as we go, and we are going to be honest at every step about which parts of the story are firmly known, which parts are strongly suspected, and which parts sit out past the edge of anything anyone can yet claim to understand. That honesty is not a weakness of the story. On this quiet channel, it is the most soothing thing I can offer you, because there is a deep and unexpected comfort in hearing someone say plainly, this part we know, and this part we do not, and we are at peace with the difference. So breathe out, and let your shoulders come down from wherever the day left them. There is nowhere to be tonight but here, following a small flame backward toward the beginning of time. And before we can ask honestly what came before that beginning, we have to be honest first about what a beginning even is, because the picture almost everyone carries of it, the great flash in the dark, turns out to be gently and importantly wrong. Let me welcome you properly now, here at the foot of the long staircase we're about to descend. Wherever you are, whatever kind of day is finally releasing you, you are welcome here. There is nothing you need to follow perfectly, nothing you need to hold on to, no thread you will lose if you drift. This is a slow walk taken together in the dark, and you are allowed to fall asleep partway down. The path will still be here, so settle into whatever is holding you, and let us begin with the thing everyone thinks they already understand, the beginning itself, because the truth of it is quieter and far more interesting than the fireworks we were all sold. When most people picture the beginning of the universe, they picture an explosion, a vast darkness, empty and waiting, and then somewhere in the middle of it a blinding flash, a fireball hurling matter outward in all directions into the surrounding void. It is a vivid image, and almost every part of it is a misunderstanding. There was no surrounding darkness for the universe to explode into. There was no central point where it happened, and no outer edge for the debris to reach. The beginning was not an event that occurred somewhere. It was, as best we can put it into plain words, the beginning of everywhere. To feel why, you have to change one deep and quiet assumption you have carried since childhood, without ever being asked to examine it. The assumption that space is a fixed and empty container, a kind of infinite room that simply exists, and that things move around inside it. That picture served us beautifully for a long time. It is the picture Isaac Newton built his physics on. Absolute space, the same everywhere and always, a silent stage on which the drama of matter plays out. But the true picture, the one we have lived with for a little over a century now, is stranger and more supple. Space is not the fixed stage. Space is part of the play. It can stretch. It can carry things apart from one another, not by pushing them through itself, but by growing between them. And when we say the universe is expanding, this is what we mean. Not that galaxies are flying apart through a static room, but that the room itself, the space between them, is quietly getting larger everywhere, all at once. There is a homely image that captures this better than almost anything. So let me hand it to you and then let it go, because we will not use it twice. Picture a loaf of raisin bread, uncooked. The dough studded through with raisins, sitting in a warm oven and slowly rising. As the dough swells, every raisin drifts away from every other raisin. Pick any raisin you like and sit on it, and you will see all the others receding from you in every direction, the far ones moving away faster than the near ones, simply because there is more swelling dough between you and them. Now here is the part that matters. No raisin is at the centre of this. There is no special raisin around which the others flee. Every raisin sees exactly the same thing, everyone else drawing away, and every raisin is equally entitled to feel like the still point of it all. The expansion has no centre inside the loaf, because the expansion is the loaf, everywhere, growing. The universe is like the inside of that loaf, except that you must let go of the crust, the outer surface, the edge of the bread, because the universe has no crust that we know of. There is only the interior, the dough, going on and swelling. Every galaxy is a raisin, and from every galaxy the view is the same, all the others sliding away, the distant ones fastest of all. When you run that swelling backward in your mind, the raisins crowd closer and closer together, the dough between them shrinking until they are packed nearly on top of one another. That crowding taken all the way to its limit is what we mean by the beginning. Not a bomb going off in a corner of a room, but the whole loaf shrunk to almost nothing, everywhere at once condensed into a single searing point that was, in a real sense, all of space rather than a place within space. This idea did not arrive gently. It arrived through one of the most quietly heroic bits of thinking in the history of science, and it was first put together in its clearest early form by a man who wore two lives at once. His name was Georges Lemaitre, and he was a Belgian priest and a trained physicist, which meant he moved comfortably between two ways of asking about beginnings that most people keep carefully apart. In the late 1920s, working from the equations of general relativity, he reasoned that if the universe is expanding today, then in the distant past it must have been smaller, and if you follow that shrinking back far enough, you reach a moment when everything was gathered into a single dense state he called the primeval atom. He had a phrase for that first moment that is so lovely, it has outlived nearly everything else he wrote. He called it a day without yesterday, a day with no day before it, a first page with no page turned to reach it. Sit with that phrase for a moment, because it is the whole of tonight folded into 4 soft words. A day without yesterday. It does not say there was darkness before, or emptiness before, or a void waiting to be filled. It says something far more careful and far more strange. It says yesterday itself may run out. It says the ladder of earlier and earlier may have a bottom rung, and that below that rung there is not a lower rung hidden in shadow, but simply no more ladder. Lemaitre, thinking as a physicist, could see this possibility written into the mathematics. Thinking as a priest, he was unusually comfortable letting a beginning be a genuine beginning, rather than insisting on some earlier stuff to explain it. And to his lasting credit, he kept the two ways of thinking scrupulously separate, and never once claimed his physics proved anything about the questions that lie past physics. That separation, that gentle refusal to overreach, is exactly the discipline we're going to hold to all night. It is worth pausing to notice that the puzzle at the heart of Lemaitre's phrase is far older than any telescope, older than physics itself, and that thoughtful people have circled it for a very long time. More than 16 centuries ago, a scholar named Augustine, writing in North Africa in the 4th and 5th centuries of our era, long before anyone dreamed the universe might have a measurable beginning, sat with almost exactly the question we are holding tonight. People in his time liked to ask, as a kind of challenge, what was happening before the world was made? What filled all that empty time before the beginning? And Augustine gave an answer of startling depth, one that reads today almost like a premonition of the physics to come. He suggested that time itself was not a fixed backdrop that had always been running, but was made along with the world, part of creation rather than a stage that preceded it. And if time itself began with the world, he reasoned, then there simply was no before for the question to point to, no stretch of empty time waiting for the world to appear in it, because there was no time at all until the world and its time began together. The question, he saw, quietly undoes itself. It asks about an earlier that cannot exist, because earlier is a feature of the very time that had not yet begun. Sit with how remarkable that is for a moment. A thinker, with no instruments, no equations, no notion of an expanding cosmos or a hot dense past, reasoned his way, by careful reflection alone, to the very insight that our deepest modern physics keeps circling back to, that the word before may need time to hold it up, and may find nothing beneath it at the very first moment. He arrived at it in the language of philosophy and faith, and we're arriving at it in the language of relativity and quantum theory, from a completely different direction, with completely different tools, and yet the shape of the insight is the same. That convergence, across 16 centuries and across such different ways of asking, is itself a quiet marvel, and a reminder that the question you carried up out of the dark tonight is one of the oldest and most human there is, asked and re-asked by every thoughtful generation, each with the tools it had. But a beautiful idea in an equation is not yet knowledge. Lemaitre had reasoned that the universe should be expanding. The next step, the step that turned a possibility into a discovery, was for someone to go outside, point an instrument at the sky, and actually catch the universe in the act of growing. And that is where the story leaves the quiet of the study and climbs a mountain in the dark, which is where we will go next. Because before we can trust any talk of a beginning, we have to see with our own eyes the single most important fact underneath it, the fact that the universe refuses to sit still. For most of human history, the night sky looked like the very definition of permanence. The stars returned each night to their appointed places. The same constellations that guided a sailor guided his great-grandchildren. If anything in all the world seemed eternal and unchanging, it was the heavens, and so it is no surprise that the finest minds assumed the universe as a whole was static, a vast and settled thing that had simply always been more or less as it is. Even Albert Einstein, who had just rebuilt our understanding of space and time from the ground up, assumed this. When he first applied his new theory of gravity to the universe as a whole, in the year 1917, the equations told him something he did not want to hear. They said the universe could not sit still. Gravity, left to itself, should pull everything together. A static universe should collapse. So Einstein did something he later regretted. He added a term to his equations by hand, a kind of cosmic counterweight, a gentle outward pressure woven into space itself, tuned precisely to hold the universe still against its own gravity. He called it the cosmological constant, and he added it for no reason other than to force the mathematics to describe the stationary universe he was sure he lived in. It was, he said to have called it much later, the greatest blunder of his life, and whether or not he used exactly those words, the lesson in it is real and worth carrying. The most careful thinker of his age looked at an equation that was trying to tell him the universe was dynamic, alive, expanding or contracting, and he overruled it because it contradicted what everyone knew. He trusted the belief over the mathematics, and the mathematics, it turned out, had been right all along. A young Russian named Alexander Friedmann had already found, a few years earlier, that Einstein's own equations, left honest and untampered with, allowed for a universe that expands, a universe with a beginning in time. Friedmann died young and did not live to see himself vindicated, but the solutions he found are still the backbone of how we describe the expanding cosmos today. The universe, the equations kept insisting, was not a still pond. It was something in motion. The confirmation came from a mountaintop in California, from a man peering through what was then the largest telescope on Earth. His name was Edwin Hubble, and through the 1920s he was doing something that sounds simple and was fiendishly hard. He was measuring how far away other galaxies are, and how fast they are moving toward us or away from us. The speed was the easier part, because light carries that information faithfully. When a source of light moves away from you, its light is stretched, shifted toward the red end of the spectrum, in the same way a train's whistle drops in pitch as it passes and speeds away. Astronomers could read that stretching, that redshift in the light of distant galaxies, and translate it into a speed. What Hubble added was distance, painstakingly worked out using certain special stars whose true brightness could be known, so that their apparent faintness revealed how far their light had travelled. And the tool that made this possible came from a quieter corner of the story, from a woman whose name deserves to be spoken far more often than it is. Her name was Henrietta Leavitt, and she worked at the Harvard College Observatory in the early years of the 20th century, one of a group of women employed to do the exacting work of measuring and cataloguing the stars recorded on thousands upon thousands of photographic plates, work considered clerical at the time and paid as such, though it demanded extraordinary patience and precision. Leavitt was studying a particular kind of star that does not shine steadily but pulses, brightening and dimming in a slow, regular rhythm, swelling and shrinking like something breathing. And she noticed a pattern so simple and so powerful that it changed astronomy forever. The stars that pulse slowly were, without exception, brighter than the stars that pulse quickly, and the relationship between the rhythm and the true brightness was so tight and so reliable that you could turn it around and use it. If you timed how long one of these stars took to complete its cycle of brightening and dimming, the rhythm alone told you how much light it was truly giving off. And once you knew how much light a star was truly giving off, You had only to compare that with how faint it appeared in your telescope to know how far away it must be, in the same way that a light of known strength seen dim across a valley tells you, by its very dimness, how far the valley reaches. This was the measuring rod the whole Enterprise had been missing, a reliable way to read the distance to things impossibly far away, and it is the rod Hubble took up and carried to the mountaintop. When he found these pulsing stars in the faint smudges of light that some astronomers still insisted were nearby clouds of gas within our own galaxy, he timed their rhythms, read off their true brightness, compared it to their apparent faintness, and arrived at distances so vast that the smudges could not possibly be inside the Milky Way at all. They were other galaxies, whole islands of billions of stars unthinkably far away, and the universe was suddenly enormously larger than almost anyone had dared to believe. Leavitt did not live to see the full harvest of what she had planted, but every measurement of cosmic distance made since rests, in one way or another, on the quiet pattern she found among the pulsing stars, and it is worth remembering as you drift that some of the deepest knowledge we have was built by careful hands whose owners were never famous in their own time. And when Hubble laid the two measurements side by side, distance and speed, he found a relationship so clean it was almost startling. The farther away a galaxy was, the faster it was rushing away from us. Twice as far, roughly twice as fast, 10 times as far, roughly 10 times as fast. This is exactly, precisely, the pattern you would see from inside the rising loaf of bread, from the surface of any raisin. It is the unmistakable signature of expansion with no centre. Every galaxy is receding, the distant ones fastest, and we're not special, because from every galaxy the view would be the same. Hubble had caught the universe in the act. It was growing. And it should be said, in fairness to the priest who saw it first, that Lemaitre had actually derived this very relationship from theory before Hubble published his measurements, which is why you will now sometimes hear it called the Hubble-Lemaitre law, a small correction of the record made gently, decades late, in honour of the man with the day without yesterday. There is a subtlety in that stretched light worth pausing over, because it is often explained a little too simply, and the truer version is more beautiful. When we say the light of distant galaxies is shifted toward the red, it is tempting to picture it exactly like the dropping pitch of that passing train, as though the galaxies were simply objects hurtling away through space, and their light lowered in pitch by their motion. That picture is not wrong, but it is not the deepest truth either. The deeper truth is that the light is stretched not because the galaxy is racing away through space, but because space itself grew while the light was crossing it. Picture a single wave of light setting out from a distant galaxy long ago, its crests marching along at a fixed spacing. As that wave travels across the universe for millions or billions of years, the space it is passing through is quietly expanding beneath it, and the wave is stretched along with everything else, its crests drawn gradually farther apart so that by the time it reaches your eye it is a longer, redder wave than the one that set out. The redness is not really a speed, it is a record. It tells you how much the universe grew during the whole long journey of that particular ray of light. Light that has travelled longer has ridden more expansion and is stretched more, which is exactly why the most distant galaxies show the greatest shift. Every reddened galaxy in the sky is, in this sense, carrying a measurement of how much larger the universe became while its light was on the way to us. A ruler not of distance alone, but of elapsed growth, written into the colour of ancient light. Once you know the universe is expanding, the road backward opens beneath your feet, and it is almost impossible not to walk down it. If everything is flying apart now, then yesterday it was all a little closer together. 1,000 years ago, closer still. 1 billion years ago, closer than that. Run the film backward far enough and the galaxies dissolve back into the gas they formed from, and that gas grows denser and hotter as you compress it, the way air warms when you pump it into a tyre, until you reach a pass that was not merely crowded but genuinely on fire, the universe filled edge to edge with searing light. This is the true meaning of the beginning that the equations point to. Not a flash in the dark, but a whole cosmos that was once a furnace, everywhere at once. Not everyone accepted this, and the resistance to it produced one of the most graceful scientific arguments of the 20th century worth telling, because the losing side was clever and sincere and wrong in an instructive way. In the middle of the century, a group of brilliant physicists, chief among them Fred Hoyle, along with Hermann Bondi and Thomas Gold, found the whole idea of a beginning distasteful. It seemed to them almost unscientific, a single, unrepeatable event you could never study, a moment that smuggled in questions science could not touch. So they proposed an elegant alternative, the steady-state universe. Yes, they agreed, the universe is expanding, but what if it had always been expanding forever, with no beginning at all? What if, as galaxies drift apart and space opens up between them, brand new matter quietly comes into being in the gaps, just enough to keep the overall density of the universe the same across all of time? In their picture, the universe was like a candle that never grows shorter, burning steadily yet never diminishing, eternal and self-renewing, always changing locally and never changing overall. It was a beautiful idea, and it had no beginning to explain, which was precisely its appeal. There is a small delicious irony buried in this quarrel, and it is the source of the very name we now use. Fred Hoyle, who did not believe in a sudden fiery origin, is the one who accidentally named it. In a radio broadcast around the year 1949, reaching for a vivid way to describe the theory he disagreed with, the theory of a universe erupting from a single dense moment, he called it, a little dismissively, the Big Bang. The phrase was catchy in a way he never intended. It stuck to his opponent's theory like a burr, outlived his own preferred picture entirely, and became the household name for the very idea he spent his career resisting. There is a lesson in that too, gentle and human, about how the words we choose escape us and go on to have lives of their own. The steady-state universe made a bold and testable promise, and this is what eventually undid it. A universe that has always looked roughly the same should look the same in the distant past as it does today, because in that picture there is no special early era, no youth, no furnace, just the eternal steady burn. But a universe that began hot and dense and has been cooling and thinning ever since must have a visibly different past. It must have been hotter long ago, and crucially, if the whole cosmos was once a furnace filled with blinding light, then that light should not simply have vanished. It should still be here, all around us, stretched by all the expansion since into something we could, in principle, detect. The steady-state universe predicted no such relic. The hot beginning demanded one. 2 pictures of everything, and one clean place where they disagreed. All that remained was to go and look, to see whether the sky still holds the faint warmth of that ancient fire. And the story of how we found it, entirely by accident, on a hill in New Jersey, with 2 annoyed engineers and a family of pigeons, is one of the most charming true stories in all of science, and it is where we're going next. In the year 1965, at a research laboratory in Holmdel, New Jersey, 2 young radio astronomers named Arno Penzias and Robert Wilson were trying to do something entirely ordinary. They had a magnificent instrument, a large horn-shaped antenna, originally built to catch faint radio signals bounced off early communication satellites, and they wanted to repurpose it for delicate measurements of the sky. To do that, they needed to understand every last source of noise in their equipment, every faint hiss and hum, so they could subtract it away and hear the true signals underneath. It was careful, unglamorous work, the kind that fills far more of science than any flash of insight ever does. But there was a problem, and it would not go away. No matter where they pointed the antenna, no matter the time of day or the season of the year, they picked up a faint, steady hiss, a persistent whisper of radio noise coming from every direction in the sky at once. It was not the sun. It was not any city. It was not the galaxy, because it did not strengthen when they aimed at the crowded band of the Milky Way. It was everywhere, evenly, always, a soft, uniform static soaking the whole sky. And it was ruining their measurements. So they set about hunting it down, convinced it must be a flaw in their own equipment. They checked every connection. They cooled their detector to reduce its own internal noise. They found that a pair of pigeons had roosted inside the great horn of the antenna and coated its interior with droppings, which Penzias delicately described in his notes as a white dielectric material, and they cleaned it out, and they even, with some regret, dealt with the pigeons themselves. And still the hiss remained, faint and patient and utterly uniform, coming from all of the sky and none of it. What they did not know, what they had no way of knowing, was that only a short drive away, at Princeton University, a group of physicists led by Robert Dicke had been working through the theory of a hot beginning, and had concluded that if the universe truly started as a furnace, its cooled and stretched relic radiation should still fill the sky today at a very particular faint temperature in exactly the range of radio waves. Dicke's group was, at that very moment, building an antenna to go looking for it. The prediction and the accidental discovery were happening in parallel, a few miles apart, unaware of each other. When a mutual acquaintance finally connected the two teams, and Penzias described the stubborn hiss he could not get rid of, Dicke turned to his colleagues and said, quietly, that they had been scooped. The noise that two engineers had been trying so hard to eliminate was not a flaw in their antenna at all. It was the oldest light in the universe, the afterglow of the beginning itself, arriving faithfully from every direction after a journey of more than 13 billion years. Let that settle, because it is one of the most quietly astonishing facts in all of science, and it deserves to be received slowly. The warmth of the newborn universe never left. It cooled and it stretched, thinned out and shifted from blinding light down through the colours and past them into the low soft register of radio, but it is still here, still washing over you this very moment, filling the room you are lying in, passing through the walls and through you and out the other side. When older televisions used to be tuned between channels, a small fraction of that grey snowy static on the screen was this, the light of the early universe, being caught by the antenna and shown to you as noise. You have almost certainly seen the beginning of time with your own eyes, and mistaken it for nothing at all. This ancient glow has a name, plain and descriptive, and I will give it to you in full because we will lean on it many times tonight. It is the cosmic microwave background. Cosmic because it comes from all of the cosmos. Microwave because that is the kind of light it has been stretched into by the long expansion. Background because it lies behind everything else, the faint uniform canvas on which all the galaxies are painted. It is the most perfect and complete map we have of the young universe, and it is the single strongest piece of evidence that the universe truly did begin hot and dense, exactly as the equations foretold, and did not simply burn on forever in an eternal steady calm. The steady-state universe predicted no such glow, and could not account for it, and so, gently and decisively, that lovely eternal candle was set aside. Fred Hoyle, to the end of his life, never fully accepted the beginning he had accidentally named. There is something almost tender in that, a brilliant man standing at the edge of a truth he could not bring himself to walk into. But here is the detail that keeps this from being the end of the story, and instead makes it the doorway to everything deeper, and it is a detail people almost always miss. The cosmic background is often described loosely as light from the beginning. That is close, but it is not quite right, and the small correction is where tonight starts to open up. This oldest light did not set out at the very first instant. It set out about 380,000 years after the beginning, which sounds like a long time but is the merest eye blink against the more than 13 billion years that have passed since. For those first several 100,000 years, the universe was so hot that it was not transparent at all. It was a dense fog of bare particles, electrons and atomic nuclei not yet joined together, and light could not travel freely through it. A ray of light in that early fog would move only the tiniest distance before colliding with a loose electron and scattering off in some new direction, over and over, endlessly, the way sunlight is scattered inside a cloud so that you cannot see the sun through it, only a general glow. The early universe was opaque, luminous but blind, a glowing fog you could not see into. Then, as the universe expanded and cooled, it crossed a threshold. When the temperature fell to a few thousand degrees, cool enough at last, the loose electrons could finally settle down and bind to the nuclei, forming the first complete neutral atoms, mostly hydrogen. And in that moment, quite suddenly on cosmic scales, the fog lifted. With the electrons tucked into atoms rather than roaming free, light was no longer constantly scattered. It could stream ahead unobstructed straight across the newly clear universe for the first time. The cosmic background is that light, released at the instant the fog cleared, the first light ever to travel freely. It is a photograph of the universe at the age of 380,000 years, the moment it became transparent, and we call that moment the last scattering, because it is the last time, for most of this light, that it bounced off anything at all before reaching your eyes tonight. Think about what has happened to that light in the ages since. When it was set free, the universe had cooled to a few thousand degrees, and light at that temperature glows a dull orange-red, the colour of a cooling ember or the surface of a cool star. If you could have stood in the universe at that moment and looked around, everything would have glowed with that soft, warm light, evenly, in every direction, a sky on fire in gentle colour. But the expansion has been at work on that light for more than 13 billion years, stretching it by a factor of roughly 1,000, and stretching light cools it in exact proportion. So the glow that was once a warm orange has been drawn out and out until it has cooled all the way down to about 2.7 degrees above absolute zero, the coldest cold there is, the temperature at which all warmth has very nearly drained out of matter entirely. It is far colder than the coldest natural place we know, colder than the shadowed craters of distant moons, so cold that we can only reach lower temperatures deliberately in careful laboratories built for the purpose. The fire of the beginning is still here, but it has been cooled by the ages into the faintest imaginable chill, a whisper of warmth spread evenly across all of space. And there is something worth noticing about where this oldest light comes from, because it gently overturns any lingering sense that the beginning happened somewhere far off, in one particular direction. This light reaches us from every direction at once, from all sides equally, which means that the moment of last scattering surrounds us completely, a vast shell of oldest light with us at its centre, like the inside of an enormous sphere whose surface is the universe at 380,000 years old. But you must not think of this as meaning we are the centre of the universe, because every observer, everywhere in the cosmos, sees exactly the same thing. Their own shell of oldest light surrounding them on all sides, their own sphere with themselves at the middle of it. There is no single centre. There is only the fact that from any point at all, the beginning lies equally in every direction, wrapped around you like a horizon that never gets any nearer no matter where you go. Because it is not a place, but a time, the earliest time we can ever see. So this oldest light is not the beginning. It is a wall. Not a wall of stone, but a wall of fog, the surface of last scattering. And it is the earliest thing we can ever directly see with light, because before it, the universe was opaque and simply cannot be looked into. Behind that wall, in those first 380,000 years, the universe was doing extraordinary things, forging the very first elements, deciding the basic recipe of all matter that would ever exist. But it did all of this hidden inside the glowing fog, where no light we could ever catch was free to carry the news outward. And here is the marvel, the thing that should pull you gently forward into the dark rather than let you rest too soon. Even though we cannot see behind that wall, we can still know what happened there. We can compute it, and then we can check our computations against faint fingerprints the early universe left in the light and in the matter around us. The wall is a flaw to our sight. It is not a flaw to our knowledge. And what lies just behind it, in the first few minutes of everything, is a story so precise and so well confirmed that it stands as one of the great triumphs of the human mind, which is exactly where we are going to step next. Past the wall of fog into the first 3 minutes of time. To go behind the wall of fog, we do not use a telescope, because there is nothing there for a telescope to see. Instead, we use something quieter, and in its own way more astonishing. We use physics itself, run backward like a careful recipe read in reverse, and then we check the results against the ashes the fire left behind. This is one of the most soothing ideas I know, so let me lay it out slowly. When the universe was young enough to be hidden inside its own glow, it was also simple. It was almost uniformly hot, almost uniformly dense, a smooth soup of the most basic building blocks of matter, and simple things are exactly the things physics describes best. The tangled complexity of a living cell or a weather system or a human heart lies far beyond our power to compute from first principles. But a nearly uniform bath of particles at a known temperature is, believe it or not, straightforward. We understand how such particles behave. We can calculate second by second what such a universe must have done as it cooled. The man who first walked this path with real seriousness was George Gamow, a Russian-born physicist with a booming laugh and a taste for mischief, who realised in the 1940s that the early universe would have been a nuclear furnace, and that its cooling could be worked out like the stages of a controlled burn. He set his student, a careful young man named Ralph Alpha, to the calculations, and together they traced how the very lightest elements would have been cooked in the first moments of time. There is a small joke buried in the history here, the kind physicists cannot resist. When Gamow prepared to publish the work, he could not stand that the author list of a paper about the beginning of everything read only alpha and Gamow, so he added the name of his friend Hans Bethe in the middle, purely so that the three authors would read Alpha, Bethe, Gamow, a soft echo of the first three letters of the Greek alphabet, Alpha, Beta, Gamma. It was a pun about the origin of the elements, smuggled into the historical record, and it has been smiled at by physicists ever since. Even at the frontier of the deepest questions, people remained people, delighted by a good joke. Here is what the calculation reveals, and it is worth going through gently, because the numbers are not just numbers, they are a recipe with a closing window. In the first fraction of a second, the universe was far too hot for any atomic nucleus to survive. It was a formless sea of the most elementary particles, quarks and their kin, too energetic to bind into anything at all. As it expanded and cooled, those particles combined into protons and neutrons, the components of atomic nuclei, roughly equal in number at first. But neutrons, when they are left on their own, are unstable. A lone neutron will, after about a quarter of an hour on average, decay into a proton. So a clock was ticking. The neutrons were slowly disappearing, converting into protons, and any that were going to be locked away safely inside a nucleus had to be locked away before they decayed. There was a window, and it was closing. For the first full second, and for a while after, the universe was still too hot for even the simplest nucleus to hold together. The moment two particles stuck, a passing burst of energy would knock them apart again. This is the bottleneck, and it is the crux of the whole story. The simplest compound nucleus, a single proton bound to a single neutron, is a fragile thing, easily shattered, and until the universe cooled enough for it to survive, nothing heavier could form, because everything heavier had to be built up through that fragile first step. So the furnace waited, hot and impatient, unable to begin cooking in earnest, while the neutrons quietly ticked away. Then, a few minutes in, the temperature dropped just low enough. The fragile first step could hold, and in a rush, in a window only a few minutes wide, the surviving neutrons and protons snapped together into the light elements, mostly a very stable nucleus of 2 protons and 2 neutrons, the heart of a helium atom. Think of it as a brief window of cooking before the oven cools past use. A cook has a pot on a flame that is dying, and only a few minutes in which the heat is right, hot enough to cook but not so hot as to burn, and whatever is not made in those few minutes will never be made, because the flame is going out and the ingredients are drifting apart in the expanding pot. That is precisely the situation the early universe found itself in. The window opened, the light elements formed in a burst, and then the universe expanded and thinned until the particles were too far apart and too cool to fuse any further. The cooking simply stopped. There is a deeper reason the furnace stalled exactly where it did, at helium, and it is one of those quiet accidents in the architecture of matter that shaped the entire character of the universe to come. To climb higher up the ladder of elements, the furnace would have needed to stack more particles onto the helium it had just made. But nature placed 2 strange breaks in the ladder right at that point. There is no stable nucleus made of exactly 5 particles, and none made of exactly 8. The arrangements that would sit at those 2 rungs are so unstable that they fall apart almost the instant they form, in a tiny fraction of a second. So the obvious next steps upward from helium, add 1 more particle to reach 5, or fuse 2 helium nuclei to reach 8. Both lead straight to a rung that crumbles underfoot. Inside a living star, given millions of unhurried years, there is a rare and delicate way to leap across this gap, a way that requires 3 helium nuclei to arrive at very nearly the same place, at very nearly the same instant, and merge together in a single stroke, skipping the broken rungs entirely. But that triple meeting is so improbable that it needs the patience and density of a stellar core held steady for ages. The first few minutes of the universe had no such patience. Everything was flying apart, thinning and cooling with every passing second, and there was simply no time for such rare and lucky collisions. The furnace reached helium, met the 2 broken rungs just above it, and could climb no further before the expansion swept all the ingredients out of reach of one another. And so, The beginning left the universe almost entirely hydrogen and helium, and left the making of everything heavier, the carbon and the oxygen and the iron, to the stars that would not be born for many millions of years. This is why the vast majority of ordinary matter in the universe to this very day is the two simplest elements, hydrogen and helium, and almost nothing else. The heavier elements, the carbon in your cells, the oxygen you are breathing, the iron in your blood, none of these were made in the beginning. They were forged much later, inside stars and scattered by their deaths. But the basic ratio, the great division of primordial matter, was settled in those first few minutes, and it has a specific value we can calculate. The calculation says that when the cooking stopped, the universe should have been left as roughly 3/4 hydrogen and about 1/4 helium, measured by mass, with only the faintest trace of a couple of other light elements mixed in. And now comes the part that turns a beautiful story into hard knowledge. We can go and measure this. We can look at the oldest, most pristine gas we can find, gas in the outskirts of galaxies that has never been through the churning interior of a star, and we can ask what it is made of. And it comes back, again and again, at almost exactly that ratio, close to 3/4 hydrogen and 1/4 helium. The recipe written down from pure calculation, run forward from a universe we cannot see, matches the composition of the actual gas floating in the actual sky. That agreement is not a small thing. It is the fingerprint of the first 3 minutes, pressed into the matter of the cosmos and still legible after more than 13 billion years. And it is one of the reasons we can speak so confidently about an era we can never directly look at. There is even, tucked into this triumph, a small, honest wrinkle, the kind this channel will never smooth over, because the wrinkles are often where the next discoveries hide. One of the light elements the calculation predicts, a form of lithium, does not quite match what we observe. The oldest stars seem to hold less of it than the recipe says they should. This is a genuine puzzle, unresolved, discussed calmly in the literature under the plain name of the lithium problem, and nobody yet knows for certain whether the fault lies in our measurements, or in some subtlety of how stars process their material, or in some gentle gap in the physics itself. It does not overturn the story. The broad agreement on hydrogen and helium is overwhelming, but it is a reminder, offered without any alarm, that even our best confirmed pictures have a loose thread or two, and that the people who study these things are perfectly at peace, holding a story that is 99 parts settled and 1 part still open. That peace is worth borrowing for your own life, on nights like this one. So we have now walked backward past the wall of fog into the first few minutes and found the universe not only comprehensible there, but astonishingly well behaved, cooking its elements on schedule, leaving fingerprints we can still read. And you might reasonably ask how anyone dares to be so confident about numbers drawn from a time before there were any atoms, let alone any instruments or any witnesses. That question deserves a whole chapter of its own, because the answer, the story of how we actually measure the early universe, is not a dry footnote to the discovery. It is, quietly, one of the most beautiful things people have ever managed to do, reading an entire history out of a whisper of light, finer than almost anything the human hand has ever detected. Return with me for a moment to that oldest light, the cosmic background, the glow released when the fog lifted. When Penzias and Wilson first stumbled on it, all they could say was that it was there, a faint uniform hiss at a certain rough temperature, the same in every direction. And that uniformity, that perfect sameness across the whole sky, was itself the first great clue, because it told us the early universe was smooth, evenly hot everywhere, with no great lumps or gaps. But a universe that was perfectly, exactly smooth would be a problem, because our universe today is not smooth at all. It is clumped into galaxies and clusters and vast empty voids. If the early universe had been utterly featureless, there would have been nothing for gravity to grab onto, no slightly denser regions to pull matter together, and no galaxies would ever have formed. So there had to be tiny irregularities in that early glow, faint patches very slightly warmer or cooler than the average, the seeds from which all structure would later grow. The theory demanded them. The great question for decades was whether we could actually see them. And here the difficulty is almost hard to overstate, so let me give you the scale of it, because the smallness is the wonder. The variations we were looking for, those faint warm and cool patches in the oldest light, differ from the average temperature by about 1 part in 100,000. Picture the finest grain of texture on an old photograph, the subtle mottling you only notice when you bring it close to a lamp and tilt it in the light. Now imagine a texture 10,000 times fainter than that, a pattern so slight that across the entire sky, the hottest patch and the coldest patch differ by less than 1,000th of a degree. That is the signal. That is what had to be measured, from the ground and eventually from space, against the roar of every other source of warmth and noise in the universe, to read the seeds of every galaxy that would ever exist. It is a little like trying to hear a single, held breath in a stadium of 100,000 people all breathing at once, and not only hearing it, but mapping exactly where in the crowd it came from. To do it, we sent instruments above the interference of the atmosphere on a lineage of satellites, each finer than the last, and I will name them the way you might name a family because they are one story across generations. First came a satellite that confirmed, with exquisite precision, that the oldest light has exactly the character a cooling furnace would leave behind, and caught the very first faint hint of those temperature ripples. Then a second, more sensitive mission mapped the ripples across the whole sky in real detail. And then a third, a European observatory named for Max Planck, the physicist who stands at the very foundation of our understanding of heat and light, and whom we will meet again before the night is done, made the finest map of all, resolving the faint texture of the oldest light with breathtaking precision. From that map and the exquisite pattern of its ripples, cosmologists could read off the fundamental properties of the entire universe, the way a geologist reads the history of a landscape in the folds of a cliff face. And this is where one of the most quoted numbers in all of science actually comes from, so let me place it in your hands gently, with its meaning attached. From the pattern in that oldest light, refined and cross-checked against many other measurements, we find that the universe is about 13.8 billion years old. Not roughly, not as a wild guess. The best current measurements pin the age of everything to within a small fraction of a billion years, which, when you consider that we are dating the beginning of time itself using the faint texture of light, released 1/3 of a million years afterward, is a precision that ought to make you go quiet for a moment. 13.8 billion years. If you tried to count off those years 1 per second, without ever sleeping or stopping, you would not finish in a single human lifetime, or in 100 of them, or in 1,000. The whole of recorded human history, every empire and every language and every song ever written down, occupies only the last few thousand years of that span, a sliver so thin that on any honest scale of cosmic time it vanishes. You might wonder how we can trust a number like that, drawn from something as delicate as the texture of ancient light, and the answer is one of the most reassuring things about how this knowledge is built, because we do not rest the age of the universe on a single measurement at all. We check it against entirely separate roads to the same place, and they arrive together. Consider the oldest stars. Certain dense old clusters of stars are among the most ancient objects we can find, and by studying the physics of how stars burn and age, we can estimate how long those clusters have been shining. The answer comes out to something like 12 or 13 billion years, which is beautifully, satisfyingly just under the age we read from the oldest light. And that is exactly as it should be, because the very first stars could only have formed some good while after the beginning, once the primordial gas had time to gather. If the oldest stars had come out older than the universe itself, we would know something was badly wrong. Instead, the two numbers sit in gentle agreement. The stars a little younger than the cosmos that made them. Two completely different methods, one from the physics of stars and one from the texture of the oldest light, quietly pointing at the same span of time. When separate paths built on separate assumptions lead to the same answer, you begin to trust that answer in your bones. There is, tucked into all this precision, a small and fascinating disagreement that I will share with you because it is exactly the kind of honest, open, unalarming puzzle that keeps the science alive, and it has a plain name: the Hubble tension. When we measure how fast the universe is expanding today, we can do it in two quite different ways. We can read the expansion rate from the pattern in the oldest light, working forward from the early universe, or we can measure it more directly and locally, by carefully gauging the distances and speeds of relatively nearby galaxies, using the pulsing stars and other reliable beacons in the modern universe. Both methods are extraordinarily careful, refined over many years by many teams, and they give slightly different answers. Not wildly different, but different by more than the small uncertainties in each method can comfortably explain. A persistent little gap that has stubbornly refused to close as the measurements have grown more precise. Nobody yet knows what it means. It may turn out to be some subtle error hiding in one of the methods, a small systematic effect not yet accounted for. Or it may, just possibly, be a genuine crack in our picture, a hint that something is going on in the universe that our current understanding leaves out, some ingredient we have not yet recognized. Cosmologists discuss it calmly, without panic, some suspecting a measurement issue, some hoping for a new discovery. All of them agreed that the honest thing for now is to hold the puzzle open and keep looking. It is a lovely reminder that even our most confident numbers have living edges, places where the story is still being written, and that the people who do this work are perfectly comfortable saying, "Here is something we have measured beautifully and do not yet fully understand." I want to pause here, because we have come a good way down the staircase, and you deserve a rest before we go deeper. Notice how far we have already travelled tonight, and how solid the ground has been under every step. We started with the simple fact that the universe is expanding seen directly in the light of distant galaxies. We ran that expansion backward and found a hot, dense past. We found the relic glow of that furnace still filling the sky, and understood it as a wall of fog, a photograph of the universe at 380,000 years. We went behind that wall by calculation, and found the light elements cooked in the first few minutes, and we checked the recipe against the real gas of the sky, and it held. And we read the age of everything, 13.8 billion years, out of a whisper of texture in the oldest light. Every one of these is settled science, textbook science, the kind of thing that does not get overturned. You're resting right now on very firm ground. Before we leave that firm ground and start down toward the places where things grow genuinely uncertain and genuinely strange, let me say one quiet thing, and then I will let it go and not mention it again. If you find something here that stills your mind at the end of the day, that lets the noise settle and gives you one calm thing to hold, then you might consider subscribing to this small channel, not as a favour to me, but as a way of keeping a quiet place lit for yourself and for others who are also lying awake, looking for something true and gentle to fall asleep to. That is all. The offer sits there, and you are free to take it or leave it, and either way you're welcome here for as long as you like. Now let us go back to the staircase, because we are about to reach the step where the ordinary story of the beginning stops being enough, and a stranger, subtler idea has to be brought in to make sense of what we see. Here is the trouble, and it is a beautiful kind of trouble, the kind that means we are close to something deep. That oldest light, the cosmic background, is almost perfectly uniform across the entire sky. The same temperature to within that one part in 100,000 no matter which direction you look. And that uniformity, which seemed at first like the most natural thing in the world, is on closer inspection deeply puzzling. To see why, consider two patches of that oldest light on opposite sides of the sky, one far to your left and one far to your right. The light from each has travelled more than 13 billion years to reach you, from opposite directions, which means those two patches are separated by an enormous distance, far too great for anything, even light itself, to have crossed in the time available. In the ordinary picture of the beginning, those two regions have never been in contact. They have never exchanged so much as a single ray of light. They sit outside each other's reach entirely in different corners of the universe that have never once communicated, and yet they are at precisely the same temperature, matched to 1,000th of a degree. How? How can two regions that have never touched, never traded any heat, never had any way to influence one another, have settled on exactly the same temperature? It is as if you found 2 cups of coffee at opposite ends of a vast house, poured by different people who never met, cooling in different rooms, and discovered that they were the same temperature not roughly, but to an extraordinary precision, again and again, everywhere in the house. You would suspect, quite reasonably, that they must once have been in contact, poured from the same pot, sharing their warmth, before being carried apart. The uniformity of the oldest light whispers the same thing. It says these distant regions must once have been close enough to touch, close enough to share their heat and come into balance, before being flung apart to the opposite ends of the visible sky. But in the simple picture of the beginning, There was never enough time for that touching to happen. This is called the horizon problem, and it sat like a small stone in the shoe of cosmology for years. There is a companion puzzle, just as strange, called the flatness problem. When we measure the overall geometry of space, the way the universe curves on the larger scales, we find that it is astonishingly close to flat, to what a geometer would call Euclidean, the ordinary geometry of a tabletop where parallel lines never meet. Now, flatness is possible, but it is knife edge. The equations say that if the early universe had been even the tiniest fraction away from perfectly flat, that deviation would have grown and grown over billions of years, curving the universe wildly one way or the other, and we would live in a cosmos visibly bent. For the universe to be as flat as we measure it today, it must have been flat in its infancy to a precision so fine it beggars belief, balanced on the knife edge with almost impossible exactness, and nothing in the simple picture explains why it should have been so perfectly balanced. It could have been anything, and it happened to be tuned to a razor. Two puzzles, then, the sameness of regions that never touched, and the impossible flatness, both pointing at the same gap in the story, both whispering that something happened in the earliest instance that the plain picture leaves out. The answer that most cosmologists now favour arrived in a rush of insight late one night in the year 1979, in the mind of a young physicist named Alan Guth. He was not even working on cosmology as his main pursuit. He was thinking about particle physics, about the behaviour of matter at unimaginably high energies, and he realised almost by accident that under certain conditions the very early universe could have gone through a brief, staggering burst of expansion, a moment in which space itself did not merely grow, but ballooned outward at a rate beyond anything before or since, doubling and doubling and doubling in a sliver of the first second, so that a region smaller than a single particle was stretched, in almost no time at all, to something larger than the entire observable universe today. He wrote in his notebook, and the phrase has become quietly famous, the word spectacular realization, underlined. He had found, in the mathematics, a way for the universe to inflate. We call the idea cosmic inflation, and you can feel immediately how it dissolves both puzzles at once, which is why it has been so hard to let go of. The horizon problem melts away, because before that colossal stretch, the regions that are now on opposite sides of the sky were packed tightly together, close enough to touch and share their heat, and come into perfect balance, and only afterward were they flung apart by the inflation to the far corners where we now find them, still carrying the sameness of that early closeness, like twins separated at birth who share a face. And the flatness problem melts away too, because inflation stretches space so violently that any curvature it began with is smoothed almost perfectly flat, in the same way that a crumpled sheet, if you could seize its corners and pull them apart with unimaginable force, would have every wrinkle and fold drawn out of it until the fabric lay perfectly smooth. Take any curved surface and blow it up enormously, and the patch you stand on looks flat, the way the ground beneath your feet looks flat even though you live on a ball. Inflation makes the universe flat by making it, for a moment, unthinkably huge. It is such a powerful idea, explaining so much with a single stroke, that inflation has become the leading paradigm for the earliest moments, refined and extended by others after Guth, notably a physicist named André Linde, who found ways to make the idea more natural and more self-consistent. And it must be said, in fairness to the idea, that inflation is not pure speculation floating free of evidence. It makes at least one prediction that has been strikingly confirmed, and this is a large part of why so many careful people take it seriously. Remember those tiny irregularities in the oldest light, the faint warm and cool patches that were the seeds of every galaxy. Inflation offers a beautiful account of where they came from. In the quantum world, as we touched on, nothing is ever perfectly smooth or perfectly still. There is always a faint irreducible jitter, a trembling of the very smallest scales. Inflation says that the universe, before its great stretch, was small enough to be governed by that quantum trembling, and that when inflation seized it and blew it up to enormous size, it took those minuscule quantum jitters and stretched them along with everything else, enlarging them from the scale of the unimaginably small to the scale of the cosmos, freezing them in place as slight variations in density from one region to the next. Those stretched jitters, in this picture, are the seeds, and here is the testable part. Inflation predicts that these seeds should appear at very nearly all sizes with very nearly equal strength, but not exactly equal, and it predicts a specific gentle tilt to that pattern, a slight preference for a little more strength at the larger scales than the smallest. It is a precise and detailed prediction about the texture of the oldest light, and when that oldest light was finally mapped in exquisite detail, the pattern of its ripples was measured and compared against what inflation had foretold. The seeds were spread across all sizes very nearly equally, just as predicted. And that slight predicted tilt, the faint preference for a little more strength at the larger scales, was there too, measured and confirmed, exactly the small departure from perfect evenness that inflation said should exist. This is not nothing. This is a bold, specific, quantitative prediction made from an idea about the first sliver of a second, checked against the finest map of the early universe we possess and found to hold. It is one of the reasons inflation, for all that it remains unconfirmed in its deepest details, is not idle guesswork, but a serious contender that has already earned real support from real measurements. The idea has skin in the game, and so far the game has gone its way, at least in this respect. But, and this is essential, and I will say it as plainly and as calmly as I can, inflation is not yet confirmed in the way that the expansion of the universe is confirmed, or the oldest light, or the recipe of the first 3 minutes. It is a beautiful, powerful, widely accepted framework that solves real problems and makes real predictions, some of which have been borne out. But it has not been nailed down. The most direct evidence people hope to find, a particular faint pattern that inflation would have stamped into the oldest light, a subtle signature of gravitational waves rippling out from that violent stretch, has proven maddeningly elusive. There was a moment some years ago when one team announced they had found it, and there was great excitement. And then, on careful checking, it turned out that the signal they had seen was not from the early universe at all, but from ordinary dust in our own galaxy, scattered along the line of sight, mimicking the pattern they sought. I tell you that not to diminish inflation, but because it is exactly the kind of honesty this night is built on, and because the way that mistake was caught is itself a thing of beauty. A claim was made, cautiously celebrated, and then subjected to relentless scrutiny by the very community that would have loved for it to be true, and found wanting and withdrawn gracefully in public. That is not a failure of science. That is science working precisely as it should, holding even its most cherished hopes to the fire, refusing to let a beautiful idea stand on a flawed measurement. Inflation remains our best account of the first sliver of a second, strongly motivated and broadly accepted, and it may well be confirmed in the coming decades as our instruments grow finer. But tonight we will hold it exactly where it belongs, as a leading idea rather than a settled fact, a doorway we can walk up to and peer through, without pretending we have walked all the way inside. And peering through that doorway, following inflation honestly to its own conclusions, we find something that its discoverers did not entirely expect, and that many still find difficult to accept, a strange and open-ended possibility that reaches far past our own beginning, into the question of whether our universe is the only one. That is where the staircase leads next, into the gentlest and most speculative territory of the whole night, a place we will visit lightly, and label carefully, and leave without overstaying. The strange consequence is this. Once you have a mechanism that makes space inflate, doubling and redoubling at a furious rate, you find it is oddly difficult to switch off cleanly, everywhere, all at once. In many versions of the idea worked out by Andre Linde and others, inflation ends in one region, settling down into a calm, expanding universe like our own, a pocket of stillness where stars and galaxies can form, while all around that pocket the surrounding space goes on inflating, faster than the calm regions can spread, endlessly, and within that still furiously inflating space, new pockets settle out here and there, each becoming its own calm universe, while the space between them keeps on inflating and spinning off yet more pockets, without end. The picture that emerges is sometimes called eternal inflation, and it suggests that what we call our universe, the entire observable cosmos, everything we have been tracing backward all night, might be only one small settled bubble in an unimaginably vast and ever-inflating ocean, one calm pocket among countless others. The reason inflation has this tendency to become endless is worth understanding, because it is the same quantum trembling we have met before, now working on the grandest possible scale. Inflation, in these models, is driven by a kind of energy woven through space, and whether inflation continues or ends in any given spot depends on the exact value of that energy there. But because of the irreducible quantum jitter, that value is never perfectly uniform. In some regions, the jitter nudges the energy down, and inflation ends there, and a calm universe settles out. In other regions, the jitter nudges it the other way, and inflation carries on. And here is the crucial thing. The regions that keep inflating are, by their very nature, expanding at a furious exponential rate, doubling and redoubling their volume again and again, while the calm pockets, once formed, expand only gently. So the inflating regions always outrun the calm ones. No matter how many pockets settle out and become quiet universes, the still inflating space between them is growing so much faster that it always dominates the total, always creating new volume faster than pockets can consume it. Inflation, once it begins, generates more inflating space than it loses forever, and that is why, in these pictures, it never fully stops. It is a process that outpaces its own ending. There is one further idea nested inside this that is strange enough to be worth a gentle mention, and speculative enough that I will flag it clearly as we go. Some physicists have suggested that the detailed laws of nature might not be exactly the same in every bubble. The precise strengths of the forces, the exact masses of the various particles, the fine details that we usually think of as fixed features of reality, might instead settle to different values in different pockets as they cool out of the inflating ocean, in something like the way water can freeze into many different crystal patterns, depending on the exact conditions when it sets. If that was so, then most bubbles might have laws quite unlike ours, laws under which stars could never form, or chemistry could never arise, or matter could never gather into anything complex at all. And ours would simply be one of the rare bubbles whose laws happen to permit stars and planets and the slow chemistry of life, not because it was chosen or designed, but because we could only ever find ourselves in the kind of universe capable of producing us in the first place. It is one proposed way of thinking about why the constants of our own universe seem so oddly suited to allowing complexity and life, and it is a fascinating idea, and it's also deeply contested, resting as it does on layer upon layer of the unconfirmed, and I offer it only as a strange possibility to turn over gently, never as a claim to believe. Picture, if it helps, a great dark pot of water held forever just at the point of boiling and never taken off the heat. Bubbles form in it, here and there, each bubble a region where the frantic energy has calmed into something stiller. But the water between the bubbles never settles. It goes on simmering, spinning off new bubbles faster than the old ones can grow, so that the number of bubbles increases without limit, and the simmering ocean never ends. Each bubble in this picture is a universe, ours is one of them, and the others, if they exist, are forever beyond our reach, because the space between us and them is inflating so fast that no light, no signal, nothing at all could ever cross from one to another. They would be, in the most complete sense imaginable, other worlds, unreachable not by distance alone but by the very structure of the space that separates us. Now I want to be very careful here, and I want you to feel me being careful, because this is the softest ground we will stand on tonight, and I will not pretend otherwise. The idea of many universes, the multiverse, is not established science. It is a possible consequence of an idea, inflation, which is itself not yet fully confirmed. It is a speculation resting on a hypothesis, and honest cosmologists treat it exactly that way, as a fascinating idea worth exploring rather than a fact to be believed. It has a deep and genuine difficulty attached to it, which is that if the other universes are forever beyond any possible contact, then it is not clear how we could ever test the idea, ever gather evidence for or against it, and a claim that can never be tested sits uneasily at the border between physics and something else. Many thoughtful physicists find the multiverse intriguing. Many others find it troubling for exactly this reason. There is no consensus, and there may never be, and that lack of consensus is not a scandal. It is simply the honest state of a question at the very edge of what we can reach. Why bring it up at all, then, on a night meant for rest? Because it speaks directly to the question we began with, and it does so from a surprising angle. If eternal inflation is real, then the word before, applied to our universe, takes on a startling new possible meaning. Before our bubble settled out of the inflating ocean, there was, in this picture, the inflating ocean itself, going on, perhaps without any beginning of its own, perhaps eternal into the past as well as the future. In that case, our universe would not be the beginning of everything, but a local event, a calming within something older and vaster that has always been inflating. The beginning we traced all night, the day without yesterday, would be only the beginning of our pocket, our bubble, and the true story would stretch back further into the endless simmer. It is one possible answer to what came before, and it is a strange and beautiful one, and it may be entirely wrong and we simply do not know, but notice, and hold on to this quietly as we go, that even this grand picture does not truly escape our question. It only moves it, because now you can ask what came before the eternal inflation, what set the endless ocean simmering in the first place, and whether it truly had no beginning, or whether it too traces back to some first moment behind which the word before finally loses its footing. The bubbles are a marvellous idea, but they are a step on the staircase, not the bottom of it. Follow our own trail, our own bubble, all the way down, past inflation, past the first sliver of the first second, and you arrive at a single place where the question can be moved no further, where the physics we have does not merely run out of evidence but runs out of itself, where the very tools we have used all night to walk backward stop working in our hands. That place has a name, and reaching it is where the whole night quietly begins to turn. To understand where the physics runs out, you have to know that everything we have used tonight to walk backward rests on two great theories, two towering achievements of the 20th century, and that these two theories, magnificent as each is on its own, do not get along. The first is the theory of gravity that redrew our idea of space and time, general relativity, the theory that told us space can stretch and carry galaxies apart. The very theory whose equations, once solved honestly, first revealed the expanding universe to us. It is a theory of the very large, of stars and galaxies and the shape of space across billions of light years, and within that vast domain it has never once been caught in error. Every test we have thrown at it, over more than a century it has passed, often to a precision that seems almost unfair. It describes the graceful bending of light around the sun, the slow shifting of a planet's orbit, the ripples in space that wash over us when distant black holes collide. In its own kingdom, the kingdom of the large general relativity reigns without a rival. The second great theory is the physics of the very small quantum mechanics, the strange and beautiful account of how matter behaves at the scale of atoms and the particles inside them. It too has never been caught in error, and it too is precise beyond reason, predicting the behaviour of particles to a dozen decimal places, underpinning every piece of modern technology you have ever touched. But it describes a world utterly unlike the smooth, certain world of relativity. In the quantum world, nothing is quite pinned down. A particle does not have a single, definite position and a single definite motion at the same time, but exists in a haze of possibilities, a spread of maybes that only resolves into a single answer when it is measured. There is an irreducible fuzziness woven into the fabric of the small, a rule sometimes called the uncertainty principle, which says that certain pairs of properties can never both be sharp at once, that the more precisely you fix one, the more the other blurs. The very small world shimmers and trembles with this built-in indefiniteness. It is not that we lack the tools to measure it exactly, it is that exactness itself is not there to be found. Now, for almost everything in the universe, this quarrel between the large and the small never comes up, because the two theories rule separate kingdoms and rarely need to meet. When you study a galaxy, gravity matters, and quantum fuzziness is far too faint to notice. When you study a single atom, quantum rules matter and gravity is far too weak to bother with. The gravity between two particles is so absurdly feeble, compared to the other forces acting on them, that you can simply ignore it, and physicists happily do. So the two theories carve up reality between them, and each stays in its own domain, and the deep contradiction between their pictures of the world stays politely out of sight, most of the time. But run the universe backward, and there is one place where the very large and the very small are forced into the same room, where they cannot avoid each other, and where their disagreement becomes not a philosophical curiosity, but a genuine crisis. As we compress the universe back toward the beginning, the entire cosmos shrinks. Everything that exists is squeezed into a smaller and smaller volume, hotter and denser at every step. And there comes a moment, walking backward, when the whole of the universe has been compressed to a scale so tiny that it is no longer large in any sense at all. The entire cosmos becomes subject to the quantum haze, the trembling uncertainty of the very small, while at the same time its density becomes so extreme that gravity, usually so feeble, becomes overwhelmingly strong. In that single instant, and only there, both theories are shouting at once, both are essential, and neither can be ignored. The large has become small, gravity has become quantum, and the two theories, asked to describe the same thing at the same time, give answers that make no sense together. This threshold has a name, and it carries the name of the very physicist whose successor observatory mapped the oldest light for us. Max Planck, working at the very end of the 1800s, discovered the first clues to the quantum world, and in doing so he noticed that you could combine the fundamental constants of nature, the speed of light, the strength of gravity, the basic unit of quantum action, into natural units of length and time and energy, units built from the deepest constants of reality rather than from any human convention like a meter or a second. These are called the Planck units, and they mark the scale at which quantum effects and gravity become equally important, the scale at which the two great theories collide. The Planck length is almost unimaginably small. If you took a single proton, itself already 100,000 times smaller than an atom, and asked how many Planck lengths would fit across it, the answer would be about 100 billion billion. It is smallness beneath smallness beneath smallness, a scale so far below anything we can probe that it sits at the very floor of meaningful measurement. And the Planck time is the stretch of time it takes light to cross that unthinkable length, which comes out to about 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second. Say that slowly to yourself and let it defeat your intuition gently, because it is meant to. It is a duration so brief that all the ordinary words for shortness give out before you reach it. When we speak of walking the universe backward to its beginning, this is as far as the walk can honestly go. We can trace the story confidently back to a tiny fraction of the first second. We can push, more speculatively with inflation, into a far tinier fraction still. But at the Planck time, that 10,000,000th of a trillionth of a trillionth of a trillionth of a second, the road itself dissolves. Not because we lack telescopes fine enough, not because the evidence has merely run thin, but because the two theories we would need to describe what is happening contradict each other precisely there, and we do not yet have a single deeper theory that contains them both, and can speak clearly about that first sliver of time. It is a little like an old map of the world, the kind drawn when much of the earth was still unexplored, where the known coastlines are inked in confident detail, every bay and headland carefully placed, and then, at the edge of the known, the ink simply stops, not a wall, not a warning. Just the clean edge of the drawing, the point past which the mapmaker had nothing true to set down, and beyond it the blank parchment. The Planck time is that edge of the map. Everything we have traced tonight lies in the inked and confident region, the expanding universe, the oldest light, the first 3 minutes, all of it firm and drawn. And then, at that first impossible sliver of a second, the ink runs out, and past it lies the unmarked parchment, the region our current physics cannot yet describe. We know the edge is there. We can walk right up to it. We simply cannot, with the tools we now hold, see what lies across it. Filling in that blank region is the great unfinished task of theoretical physics, and it has a name: the search for a theory of quantum gravity, a single, deeper framework that would unite the very large and the very small, that would tell us how gravity itself behaves when it becomes quantum, how space and time themselves behave when they are squeezed to the Planck scale. Several candidate frameworks exist, and I will name them lightly, the way you might point at distant lights without pretending to know which house is which, because none of them is confirmed and I will not dress speculation as knowledge. One approach imagines that the most fundamental things are not point-like particles at all but tiny vibrating threads, and that the different notes such a thread can sound appear to us as the different particles of nature. Another approach imagines that space itself is not smooth and continuous, but woven from tiny discrete loops, a fabric with a smallest possible stitch, so that even space has a grain if you look closely enough. These are serious, deep, mathematically rich frameworks, pursued by brilliant people for decades, and not one of them has yet made a confirmed prediction that lets us choose between them, because the scale where they would differ, the Planck scale, is so far beyond any experiment we can build that testing them directly remains, for now, out of reach. It is worth understanding why uniting these two theories is so uniquely hard, why it has resisted the finest minds for the better part of a century when so many other unifications in physics eventually yielded. The other forces of nature, the ones that hold atoms together and make them glow, all act within space and time, playing out upon the fixed stage of the cosmos, and we learned, with great effort but real success, how to make them quantum by letting their fields tremble and shimmer against that steady backdrop. But gravity is different in a way that goes to the root of everything. Gravity, as the theory of relativity taught us, is not a force acting upon the stage. Gravity is the stage. It is the shape of space and time themselves, their curving and stretching. And so to make gravity quantum is not to add a little trembling to something moving across a fixed stage. It is to make the stage itself tremble, to let space and time themselves become uncertain and shimmering and without definite form, to pull away the very floor on which all our other physics stands. Our usual tools assume a smooth, fixed, well-behaved space and time in the background. And when you turn those tools on gravity itself, on the background itself, they fall apart in your hands, throwing up infinities and nonsense, answers that cannot possibly be right, because you have asked the mathematics to describe a situation in which the thing it needs to assume, a stable stage, is the very thing that has come undone. And there is a second signpost pointing to the same edge, one built into relativity itself, which is quietly remarkable, because it means the theory contains an honest confession of its own limits. When the equations of general relativity alone are followed backward toward the beginning, they do not simply continue smoothly forever. Under very general conditions, it was proven, with real mathematical rigour, that they must reach a point where the quantities they describe, the density, the curvature of space, climb toward the infinite, a point where the theory can no longer say anything sensible at all, a kind of mathematical cliff at the very start of time. And most physicists read that cliff not as a real feature of the world, not as an actual infinity that truly occurred, but as general relativity speaking honestly about the boundary of its own competence, raising its hand and saying, "Here, at the very beginning, my description fails, and something deeper than me must take over, something I cannot provide." A theory that predicts its own breakdown is not a broken theory. It is a truthful one, marking clearly the door beyond which it cannot go, and pointing through that door toward the quantum gravity we have not yet found. Here is why all of this matters so much for the question we started with, and here, quietly, without any single dramatic moment, is where the whole night begins to turn. All along, we have been treating time as a given, as the stage on which the story of the universe unfolds, a river already flowing under our feet, and we have been walking backward along that river toward its source. But in the extreme conditions of the Planck era, time may not be a stage at all. It may be something that itself emerges from the underlying physics, something that comes into being along with space and matter, rather than a pre-existing backdrop against which they appear. In several of the candidate theories of quantum gravity, time is not fundamental. It is not the bottom layer of reality. It is a feature that arises, that condenses out of a deeper and more timeless description in something like the way temperature arises from the motion of countless molecules, a real and useful idea at the everyday scale that simply has no meaning for a single particle. And if time itself is emergent, if it comes into being rather than always having been there, then the ground beneath the word before finally gives way. To ask what came before the beginning is to ask what came earlier than the earliest moment, but earlier is a relationship within time, a comparison that only means something if there is a river of time already flowing to place the two moments along. If time itself begins at the beginning, if there simply is no time behind the first moment for the word, before to reach into, then the question is not answered so much as gently dissolved. It is the same shape as asking what lies north of the North Pole. The question is grammatically perfect. Every word is in its place. But the thing it reaches for is not hidden or unknown. It is absent, in the deepest and most peaceful way, because you have reached the place where the very direction the question points simply stops existing. Notice that this is not a claim that there was nothing before, in the sense of a great dark emptiness waiting. An emptiness would still be a something, a stage, a where and a when in which nothing happened. What the emergence of time suggests is subtler and calmer than that. It suggests that the question itself, the reaching backward, runs out of world to reach into that before is a word that needs time to hold it up and finds, at the very first moment, that there is no more time beneath it. This is not a frightening emptiness. It is more like the quiet you feel when a long question you have carried for years finally reveals that it was, all along, the wrong shape, and that the peace you were seeking was never going to come from answering it, but from seeing it clearly enough to set it down. We're not there yet, not fully, but you can feel the ground beginning to shift, the river beginning to run out ahead of us rather than behind. And there is one particular way of making this idea precise, one beautiful and specific proposal that turns this vague sense of a dissolving before into actual mathematics, and it came from one of the most remarkable minds of our age, working with a colleague on a question most physicists had been content to leave alone. In the year 1983, two physicists set out to do something that sounds almost impossibly ambitious. James Hartler and Stephen Hawking asked whether it might be possible to describe the entire universe, including its beginning, in the language of quantum mechanics, and to do so in a way that did not require a first moment where the laws of physics break down, no sharp edge, no point where the equations simply give up and hand you an infinity. They wanted a beginning that was smooth, complete, self-contained, a universe that did not need anything outside itself or before itself to get started, a universe whose beginning was written entirely in its own laws. And the proposal they arrived at is one of the strangest and most elegant ideas in all of cosmology, and I want to walk you through it slowly, because it is subtle, and because when it finally comes into focus it does something lovely to the question we have been holding all night. Begin with the sheer audacity of what they were attempting, because it is worth feeling before we get to the mechanics. Quantum mechanics, that shimmering physics of the very small, has a peculiar way of describing how things get from one state to another. In the ordinary world, we imagine a thing follows one definite path. A ball arcs through the air along a single trajectory, and that is that. But in the quantum world, in one powerful way of thinking about it, a particle does not follow a single path at all. Instead, it explores, in some sense, every possible path at once, every route it could conceivably take, and what we finally observe emerges from the blending together of all those possibilities, some of them reinforcing one another, some cancelling out, until a single outcome crystallizes from the sum of all the ways it might have happened. To describe a quantum system fully, you do not track one history. You add up all the histories, every way the thing could have gotten from here to there, weighting each and letting them combine. Now here is the staggering leap that Hartley and Hawking made. What if you applied that same way of thinking not to a single particle, but to the entire universe? What if the cosmos as a whole does not have one definite history stretching back to a single definite beginning, but is instead described by a blend of all its possible histories, all the different ways it could have come into being and grown, added together the way the paths of a quantum particle are added together? This is what physicists mean by the wave function of the universe, and the phrase should stop you for a moment, because it treats the whole of everything, all of space and time and matter, as a single quantum object, a thing described by the same shimmering mathematics of possibility that governs an atom. It is one of the boldest ideas anyone has ever seriously proposed, and it is hard for reasons that go to the very frontier we discussed a moment ago, because to add up all the possible histories of a universe, you need to know how gravity behaves in the quantum world, and that, as we said, is precisely the thing we do not yet fully understand. But suppose you press ahead anyway, as Hartley and Hawking did, and you ask which histories to include in the sum. This is where their proposal gets its name and its beauty. Rather than summing over histories that begin at some sharp, jagged edge, some singular first point where everything is undefined, they propose that you sum only over the smooth, complete, rounded geometries, the ones with no edge and no boundary at all, the ones that close up on themselves gently like the surface of a sphere. Include only the histories with no ragged beginning, and add them all together, and what emerges from the sum is a universe that comes into being smoothly, completely, without any first moment where the laws break down. The no boundary in the name is exactly this instruction, to consider only the possible beginnings that have no boundary, no edge, no sharp first instant, and it is from that instruction that the whole gentle picture flows. The heart of the idea involves a mathematical move that sounds like sorcery, and is in fact ordinary in the deeper parts of physics, a way of treating time near the very beginning as though it behaved less like time and more like another dimension of space. In our everyday experience, time and space feel utterly different. Space is the dimension you can move around in freely, forward and back, left and right, up and down, all directions equally open. Time is the dimension you can only move through one way, always forward, never back, the dimension that carries the deep difference between before and after. In the ordinary description of the universe, that difference between time and space is built in from the start. But Hartley and Hawking explored what happens if, as you approach the very beginning, that sharp distinction softens, if time gradually loses its special one-way character and becomes, near the first moment, just another space-like direction, one more dimension with no built-in arrow, no before and after, no flow. They gave this idea a name that sounds forbidding and is really just a mathematical label, imaginary time, borrowing a term from a branch of mathematics where it has a precise and unmysterious meaning. Do not let the name trouble you. It does not mean unreal time or fictional time. It means time treated near the beginning with the same mathematics we use for a direction in space, so that it becomes smooth and directionless right at the origin, before blending into the ordinary flowing time we know as the universe grows. And the consequence of this softening is extraordinary. If time becomes space-like near the beginning, then the universe can be finite in its past, can have only so much history behind it, and yet have no first moment, no sharp edge, no singular point where everything breaks down. It can be bounded but without a boundary, complete but without an edge, the way the surface of the Earth is finite in area and yet has no border you could ever walk off, no edge of the world, no last place. And this is exactly where Hawking reached for the image that captures the whole idea more gently than any equation, an image I have been saving for you all night, because it is the perfect companion to the North Pole we keep returning to. Ask yourself, he suggested, what lies south of the South Pole. You can walk south across the whole face of the Earth, further and further south, and it is a perfectly sensible journey the whole way until you arrive at the southernmost point, the very bottom of the world, and you stand there and you ask, now, which way is further south? And there is no answer, not because the information is missing, not because south has been hidden from you, but because you have reached the place where south itself simply ceases to mean anything. There is no further south. The direction has run out, and yet nothing dramatic has happened at the pole. There is no wall there, no cliff, no edge you could fall off. The ground is perfectly ordinary. It is only the question that has come to its natural and peaceful end. In the no-boundary picture, the beginning of the universe is like the South Pole of time. As you trace time backward toward the beginning, you eventually reach the earliest moment, and if you try to ask what came before it, the question simply loses its meaning, the way further south loses its meaning at the pole. There is no before, not because before has been erased or hidden, but because you have reached the place where the direction the word points has smoothly, gently run out. The universe, in this picture, has a finite past and no first cause, no edge, no moment where something had to reach in from outside and light the fuse. It contains its own beginning entirely, the way the sphere of the Earth contains its own southern tip, needing no edge and no outside to complete it. It is a beginning without a beginning, a first moment that is not really first because there is no place before it for firstness to be measured against. I want to hold this carefully because it is beautiful and I do not want to oversell it. The no-boundary proposal is exactly that. A proposal, a serious and elegant and deeply considered hypothesis, put forward by two of the finest minds in the field and taken seriously by many and doubted by many others. It is not confirmed. It rests on that move of treating time as space-like near the beginning, a move that is mathematically well-defined but whose connection to the reality we actually live in is not settled. There are physicists who find it profound and physicists who find it a mathematical trick, and there are technical debates about whether the idea even predicts the kind of universe we observe, debates that are genuinely unresolved. So we hold it where it belongs, in the region past the edge of the map, as one carefully drawn guess about what the unmarked parchment might contain, offered by people who understood better than anyone how little we truly know about that region. But even as a guess, it does something precious. It shows that the dissolving of before is not mere hand-waving, not a philosopher's dodge. It can be made precise. There is real mathematics in which the beginning of time is like the South Pole, complete and edgeless, and needing nothing before it. And that alone should change how the original question sits in your mind. Because here is what the no-boundary idea quietly teaches, whether or not it turns out to be the true description of our universe. It teaches that when you finally reach the beginning, the most natural thing to find is not a wall with something menacing on the other side, and not a great emptiness waiting to be explained, but a smooth and self-contained completeness, a place where the questions we bring with us, the questions built out of before and after and cause and earlier, simply arrive at their own gentle horizon and rest. The universe may not need a before any more than the Earth needs an edge. And if that is so, then the vague unease that so often attaches to the question, the feeling that there must be some dark, waiting nothing behind it all, was never pointing at anything real. It was only the shadow cast by a word that had wandered past the end of its own meaning. But the no-boundary idea is not the only door left open in that unmarked region, and some of the others answer our question in a completely different spirit, not by dissolving the before, but by filling it with an entire previous world, and those doors deserve to be opened too, gently, before we come to rest. There is a whole family of ideas, entirely different in spirit from the no-boundary picture, that answer our question not by dissolving the before, but by populating it, by proposing that there was indeed something earlier, and that it was an entire universe of its own, or perhaps an endless succession of them. These are the cyclic and bouncing cosmologies, and they arise from a very natural discomfort. When our simplest equations, the ones from general relativity alone, are followed all the way back to the very first moment, they do not hand us a graceful South Pole. They hand us an infinity, a point where the density becomes unbounded and the mathematics breaks down completely, a place physicists call a singularity. And most physicists regard a singularity not as a real feature of the world, but as a warning sign, a flag that our current theory has been pushed past its limits and is no longer to be trusted. Nature, the intuition goes, does not actually do infinities. When your equations produce one, it usually means you are missing some deeper piece of physics that would smooth the infinity away. The bouncing cosmologies take this intuition seriously and ask a simple, bold question. What if the beginning was never a true beginning at all, but a bounce, a moment when a previous universe, contracting, growing denser and hotter as it collapsed, reached some limit where the collapse reversed, where the crushing turned into expansion and became the outward rushing universe we now inhabit. In this picture, our beginning, the hot dense state we have traced backward all night, was not the first moment of everything, but the turning point of something older, the bottom of a great breath. Where the ordinary picture sees an edge, the bouncing picture sees a hinge. And the appeal of this is easy to feel, because a bounce needs no first cause, no lighting of a fuse, no edge of the map. It only needs a previous phase, and that previous phase can have had its own previous phase, and so on, perhaps without end. One version of this idea grows directly out of one of those candidate theories of quantum gravity, the one that imagines space is woven from tiny discrete loops, with the smallest possible stitch below which it cannot be divided. If space has a smallest stitch, then there is a limit to how much you can compress it, a point beyond which it simply cannot be squeezed any tighter, because there is no finer grain to squeeze into, and when a contracting universe reaches that limit, the story goes, the relentless inward crush meets an equally relentless resistance, a kind of pressure from the granular structure of space itself, and the collapse rebounds. What looked, in the old equations, like an infinite crush at a single first moment, becomes instead a finite, extreme, but survivable bounce, a previous universe passing through its densest instant and emerging on the far side as our own expanding cosmos. In this loop cosmology, as it is called, the singularity is replaced by a bounce, and the beginning becomes a doorway between two worlds rather than the edge of one. There is another, quite different cyclic idea, developed with great care by the physicists Paul Steinhardt and Neil Turok, which imagines our universe as one in a long, perhaps endless series of cycles, each beginning in a hot, dense state, expanding and cooling and forming galaxies, then slowly emptying and stretching over immense stretches of time, before somehow being renewed into another hot, dense beginning, another cycle, again and again. Their version draws on some of the deeper ideas from the theory of vibrating threads, picturing our entire three-dimensional universe as a kind of sheet or membrane floating in a space of more dimensions than we can see, and the beginning as a gentle collision between two such sheets, a collision that fills each with heat and matter and sets a new cycle in motion. What is elegant about their proposal is that it tries to solve the very same puzzles inflation solves, the sameness of distant regions, the flatness of space, but without a burst of inflation, achieving the smoothing instead through the slow contraction of the previous cycle. It is, in a sense, a rival to inflation, a completely different account of why the universe looks the way it does, and the two camps have argued the question with great vigour and great mutual respect for many years, without either side yet being able to deliver the decisive evidence that would settle it. And there is a third vision, perhaps the strangest and most poetic of all, put forward by Roger Penrose, one of the deepest geometric thinkers in the history of the subject. Penrose noticed something curious about the very far future of our own universe. If the current expansion continues and even accelerates, as our best measurements suggest it will, then in an unimaginably distant future the universe will grow cold and empty and dark, all its stars burnt out, all its matter dispersed, until at last even the most massive things have decayed away, and nothing remains but light, drifting through an endless, featureless, ever-expanding void. And here Penrose made a strange leap. In such a final state, he pointed out, a universe with nothing in it but massless light, there would be no clocks and no rulers left, nothing with mass to mark the passage of time or the measure of distance, and without clocks and rulers, without anything to establish a scale, the difference between unimaginably vast and unimaginably tiny might simply cease to matter. The cold, empty, enormous end of one universe might be mathematically indistinguishable, he argued, from the hot, dense, tiny beginning of another, so that the far future of one cosmos could become, seamlessly, the Big Bang of the next. Penrose calls this conformal cyclic cosmology, and he imagines the whole of existence as an endless sequence of what he calls aeons, each a complete universe, born from the death of the one before, dying into the birth of the one after, an unbroken chain reaching backward and forward without limit. It is a breathtaking vision, and Penrose, being a careful physicist as well as a bold one, has even proposed ways it might be tested, suggesting that faint circular patterns in the oldest light might be echoes of great events, like colliding black holes from the eon before ours, ripples that survived the transition from one universe to the next. Some researchers have reported seeing hints of such patterns. Others, looking at the same data, find nothing beyond what chance alone would produce. The question remains open and contested, argued back and forth in the careful language of statistics, and no consensus has formed. It is exactly the kind of claim that this channel treats with gentle caution, fascinating, unresolved, and not to be believed simply because it is beautiful. What all of these cyclic and bouncing ideas share is a particular answer to our question, and it is a startling one when you sit with it in the dark. In these pictures, the word before does have a meaning after all, and what it points to is not a void, and not a dissolving horizon, but a whole other universe, a previous cosmos, with its own long history, its own expansion, perhaps its own stars and its own structure, that contracted or transformed into ours. What came before the universe, in the cyclic view, is another universe, and what came before that one is yet another, back and back, a chain of worlds, each the ancestor of the next. In this picture, our beginning is not the beginning of everything but a single turning in something far larger and older, one breath in a rhythm that may have been going on forever, one turn of a tide whose ebb and flow we can see only the nearest edge of. Hold that image lightly for a moment, the image of a single breath. Perhaps our entire universe, all 13.8 billion years of it, all its galaxies and all its light, is a single slow breath drawn in and let out. One exhalation in a rhythm of countless breaths stretching back beyond any first breath at all. Or perhaps it is a single turn of a vast tide, and the hot dense beginning we traced all night was the moment the water, having rushed all the way in, paused and began to rush back out, a turning we mistook for a source because we could see only our own stretch of the shore. It is a gentle and a spacious way to imagine our place in things, not as the whole of existence flaring into being from nothing, but as one movement in something patient and enormous, and perhaps without end. But I must be as honest here as I have tried to be all night, and the honesty is itself a kind of rest, so receive it that way. Not one of these bouncing or cyclic pictures is confirmed. Every one of them lives out past the edge of the map, in that unmarked region where our tested physics cannot yet go, and every one of them depends on some piece of quantum gravity that we do not yet possess and cannot yet check. The loop cosmology depends on space truly having a smaller stitch, which is itself unproven. The colliding sheets depend on extra dimensions we have never observed. Penrose's endless aeons depend on a bold assumption about the far future, and a contested reading of faint patterns in the sky. These are not established facts about what came before. They are careful, serious, mathematically developed guesses offered by people at the very frontier about what the blank parchment might hold, and they disagree with one another, and they disagree with the no-boundary picture, which says there was no before at all, and there is at present no measurement fine enough to tell us which of them, if any, is right. That disagreement, that open, unsettled multiplicity of answers, is not a failure, and it is not a cause for unease. It is simply the true shape of the frontier, and there is something worth treasuring in seeing it clearly. We have walked tonight from the certain into the uncertain, step by careful step, and we have now reached the place where the honest thing is to lay several possibilities side by side and say calmly, any of these might be so, and we do not yet know, and we may not know for a very long time, and some of it we may never know at all. There is a peace available in that sentence that is not available in a false certainty. A person who insists they know exactly what came before the universe is, whatever else they are, not being straight with you. A person who says here are the possibilities, here is what each would mean, and here is the honest extent of our ignorance, is offering you something far more trustworthy and far more restful than an answer. They are offering you the truth of the situation, which includes, at its heart, a spaciousness, an openness, a room left deliberately unfilled. And so, with the doors laid open, the door that dissolves the before and the doors that fill it with earlier worlds, only one thing remains to be done tonight, and it is the gentlest task of all. It is to gather up everything we have walked through and to sort it, calmly and without hurry, into what we truly know, what we reasonably suspect, and what may lie forever past the reach of knowing, and then to bring the whole vast question home, out of the depths of cosmic time, back to the small warm fact of you, lying here in the dark, made of the very stuff whose story we have been telling. So let us sort it gently, the way you might sort a drawer at the end of a long day, unhurried, setting each thing where it belongs. And let us begin with what we truly know, because it is a great deal, and it is worth resting your weight on before we drift out toward the edges again. We know, as surely as we know anything about the world, that the universe is expanding, that the galaxies are drawing apart as the space between them grows. This is not an inference from a single measurement, but a fact confirmed 1,000 times over in the stretched light of distant galaxies, in the careful mapping of their distances and their speeds, a fact so well established that it is simply part of the furniture of modern knowledge. We know that this expansion, run backward, points to a past that was hotter and denser than the present, and we know this not merely because the equations say so, but because the relic warmth of that hot past is still here, filling the sky, the oldest light, discovered by accident and confirmed by exquisite measurement, a photograph of the universe as it was 380,000 years into its life. We know that in the first few minutes, before that photograph was taken, the lightest elements were forged in a cooling furnace, and we know it because the recipe we calculate from pure physics matches the composition of the most pristine gas we can find, roughly 3/4 hydrogen and about 1/4 helium, the fingerprint of the first 3 minutes still legible in the matter of the cosmos, and we know from the faint texture of that oldest light that the whole of this has been unfolding for about 13.8 billion years. All of this is settled. All of this is textbook. None of it is likely ever to be overturned, only refined. You may rest on it completely. Then there is the second category, the things we strongly suspect, the leading ideas that are widely accepted and well motivated but not yet nailed down with the same finality. Chief among these is inflation, that brief staggering burst of expansion in the first sliver of a second, proposed to explain the sameness of distant regions and the flatness of space, and accepted by most cosmologists as the best account we have of the earliest confirmable moments. Inflation is powerful and elegant, and it has passed real tests, and it may well be confirmed in the coming decades, but it is not yet certain, and honest people hold it as a strong hypothesis rather than a settled fact. It sits in that middle drawer, the drawer of things that are probably true, or true in something like their current form, but still awaiting the decisive evidence that would move them up into the first drawer with the expansion and the oldest light. And then there is the third category, the frontier, the region past the edge of the inked map, where our tested physics gives out and we are left with careful, serious, unconfirmed guesses. Here lies everything about the very first sliver of the first second, the Planck era, where the physics of the very large and the very small collide, and we have no single theory to describe what happens. Here lie the candidate theories of quantum gravity, the vibrating threads and the woven loops, deep and mathematically rich, and not one of them yet confirmed. Here lies the no-boundary proposal, with its beautiful idea of a beginning that is like the South Pole of time, complete and edgeless and needing nothing before it. Here lie the bouncing and cyclic pictures, with their previous universes and their endless breaths. And here, at the very deepest point, lies our original question itself, the question of what came before, which we can now see does not have a single settled answer, but instead splits into a small family of possibilities, each pointing to a different picture of reality, none yet decidable. And I want to name, honestly, that some of what lies out here may not merely be unknown but unknowable, and to say clearly what that careful word means and does not mean. If our own universe truly began at a first moment, with time itself emerging there, then the question of what came before may have no answer, not because we are ignorant, but because there is no fact of the matter to be ignorant of, the way there is no fact about what lies north of the North Pole. And if there are other universes, other bubbles in an eternal inflation, or other aeons before ours, that are forever cut off from any possible contact, then their existence, real or not, may lie permanently beyond any test we could ever devise, and a question that no possible observation could ever bear on sites at the very border of what physics can properly speak about at all. These are not gaps that a better telescope will one day fill. They may be genuine horizons, edges built into the structure of knowledge itself. And I offer that to you not as a sorrow, but as a strange kind of gift, because there is a deep and unexpected peace in reaching the honest limit of a question and being able to say, with no anxiety at all, this may be as far as anyone can ever go, and that is all right. Let yourself feel, for a moment, how remarkable it is that we can say even this much, that we can sort the drawer at all. Consider what it took. Consider that a species of warm-blooded creatures, living on the surface of one ordinary planet around one ordinary star, for a mere sliver of the universe's history, has managed to look out at the sky and read from it the age of everything, the temperature of the first light, the recipe of the primordial elements, the very expansion of space itself. We did this with no way of stepping outside the universe to look at it, no vantage point beyond it, nothing but the light that happened to fall on us, and the patient application of reason to that light. We built instruments to catch a glow released before there were any atoms to see it. We calculated the behavior of a furnace that cooled 13 billion years before the first human drew breath, and then we found its ashes in the sky and checked our sums against them, and they agreed. The wonder of tonight is not only the universe, it is also the strange fact that the universe has, in us, become able to know a little of its own beginning. The oldest light travels for 13 billion years, and falls, at last, upon a creature that can understand what it is. There is something in that worth holding gently as you drift, something that has nothing to do with pride, and everything to do with belonging. And here is where I want to bring the whole vast story home to you, out of the depths of cosmic time and into the small warm space where you are lying, because the connection is not a metaphor, it is the plainest physical fact. You are made of the beginning, not in a poetic sense, but literally, atom by atom. Recall that in the first 3 minutes the universe forged its hydrogen, and that hydrogen has been the most common substance in the cosmos ever since, the raw material of stars and the most abundant element in your own body by number of atoms. Every molecule of water in you, every drop of it, the water in your blood and your cells and on your lips, is built from hydrogen and oxygen, and that hydrogen, almost every atom of it, was made in the first 3 minutes of time. It has never been made since. The furnace that produced it cooled and closed after those first few minutes and has never reopened. Which means the hydrogen in the water you drank today, the hydrogen woven through every cell of the body that is holding you up right now, is very nearly as old as the universe itself. Forged in that cooling furnace before there were any stars, and it has been travelling ever since through clouds and stars and space for 13.8 billion years to arrive, at last, as part of you. And the rest of you, the heavier atoms, the carbon that forms the backbone of every molecule of life, the oxygen you are breathing in this very moment, the nitrogen and the phosphorus and the calcium in your bones, these were not made in the beginning. They were made later, in the hearts of stars where lighter elements were fused into heavier ones over millions of years, and then scattered across space when those stars died, some quietly, some in tremendous explosions that seeded the surrounding darkness with the freshly minted stuff of future worlds. The iron in your blood was cooked in the cores of stars that lived and died before our sun was born. The calcium in your teeth, the carbon in every strand of you, all of it was assembled in stellar furnaces and cast out into space, drifting for ages, gathering slowly under gravity into new clouds, new stars, new planets, until at last some of it gathered here, into a world with oceans, and then into living things, and then, by a long and patient chain of gathering, into you. You are, quite exactly, a temporary arrangement of ancient matter, some of it from the first minutes of time, some of it from the deaths of stars, briefly gathered into a shape that can wonder about where it all came from. Sit with that softly, because it changes the whole question we began with. You asked what was there before the universe, as though the universe was something out there, distant, separate, a thing to be inquired about from the outside. But you're not outside it, you are the universe, a small folded piece of it, made of its oldest atoms, warmed by its ancient light, briefly conscious, lying in the dark asking about your own origin. The particles in your resting hand are very nearly as old as everything there is. When you close that hand, you are closing it around some of the oldest matter in existence, matter that has been on an unbroken journey since a time when there were no stars and no planets, and no before that anyone can point to. You have never been separate from the beginning. You are one of the places the beginning ended up. And so the great question, the one we have carried all night, comes to rest not as an answer but as a transformation, which is exactly what I promised you it would do, back at the very top of the staircase. We did not find a scene from before the beginning. We found something better and quieter and truer. We found that the word before, followed all the way down, either dissolves gently at a horizon like the South Pole of time, where the direction it points simply runs out, or opens onto a whole other world, a previous universe, one turn in a rhythm we can see only the nearest edge of, and we found that we cannot yet say which, and may never be able to, and that this uncertainty is not a wound but a spaciousness, a room left open, an honest edge to what a mind can reach. The question you started with was built out of a word that needs time to stand on, and when you carried it all the way back to where time itself grows thin, the word did not find an answer. It found its own gentle limit. And the unease that so often clings to the question, the sense that there must be some dark waiting nothing behind everything, turns out to have been only the shadow that word cast when it wandered one step past the end of its own meaning. There is nothing behind the beginning to fear, and perhaps nothing behind it at all in the way the question imagined, and if there is something, it is another world as full and as real as this one. And either way you are held right now, inside a cosmos that has been unfolding for 13 billion years and will go on unfolding in most pictures for a future so long that the entire past we have discussed tonight is only its first faint morning. The universe is not running out. It is by every measure we have immensely young, and you are here near the very beginning of a story whose middle and end lie unthinkably far ahead. That is not a thought to trouble your rest. It is a thought to rest inside, the way you might rest inside a large quiet house, knowing the rooms go on far beyond the one you are in, and that there is no need, tonight, to visit them all. Let your breathing slow now, if it has not already. Let the numbers go. You do not need to carry the 13.8 billion years, or the 380,000, or the first 3 minutes, or the impossible sliver of the Planck time. You do not need to hold the bubbles or the aeons or the South Pole of time. They will keep. They have kept for ages without you, and they will keep through the night while you sleep, and they will still be here, exactly as strange and exactly as gentle whenever you wish to return to them. All that was ever needed tonight was for you to feel, once, quietly, that the question you have carried since childhood is not a locked door with something frightening behind it, but an open horizon, and that you yourself are made of the very thing you are asking about, and that this is enough. The oldest light is still arriving. Even now, as your eyes grow heavy, that faint glow released 380,000 years into the life of the universe is falling on the world around you, passing through the walls, passing through the air, passing gently through you and onward, the way it has for 13 billion years and will for billions more. You are lying in the middle of it, bathed in the afterglow of the beginning, made of atoms nearly as old as time, a small warm gathering of the universe's oldest matter, briefly awake, now softly letting go. And there is nothing you need to do, and nowhere you need to be, and no question left to answer, only the quiet and the ancient light, and you, here in the dark, older than you ever knew, and perfectly finally at rest.